a reduced version of that Jacobian by utilizing both an eigenvalue decomposition as a scaling factor. So for determining curl and deviation with respect to the local instantaneous gradient. But for a given space, establishing ideal parameterization for the learning rate, right, is going to be establishing that step size characteristic. Now, if we use a fixed step size characteristic for the entire gradient, that's pretty much what we were doing when we did it last time, right? So when you guys did your assignment for your neural network training process, you picked a fixed step size, and at every particular instance in which you were doing a back propagation, you utilized that scaling factor to change relative to that gradient. What happens whenever that gradient starts to get relatively small? If you have a small learning rate with a small gradient, it's going to slow down, okay? That's related to this concept that we're talking about called momentum, right? So the momentum of the component is a bit like dropping a marble down a line, right? When it gets to a region that has relatively flat area, it's going to slow itself down because it's not getting a lot of forward movement from the instantaneous gradient for the local space because there may not be much of a local instantaneous gradient, right? You can get into an area in which no matter where you move around, it's still relatively flat, okay? Then you get to an area where it's like a sheer cliff face and you drop straight off into it, okay? So those are the nice areas. Those are the areas where we see our error drop dramatically, right? But oftentimes it can go, you're screaming down the gradient, you're like learning, you know, it's just learning, doing great. And then all of a sudden it just plateaus, right? Just a slow process, slow slog. So we're gonna have some tricks. We're gonna have to do something to that to try to resolve that problem because those plateaus can get big. We have a very large search area and we have a lot of parameters. There's an interesting relationship here in the effect that we are calculating all of the partials with respect to the dimensional characteristics. And if we do that second order partial characteristic, we can get a lot of description about the curl of the space that can give us an idea of whether or not we're stuck in saddle points, low points, optimization points, etc. Well, that's the estimations that I'm going to do as kind of an add-on. But this notion says that learning rate, if you think about it from this perspective, learning rate may be one of the more important components of figuring out how to learn within a system, right? There have been some theories that I've looked at, there have been some talks that I've been to, and they're related to this idea that when the network starts off, and it's relatively naive, when it has a lot of error to play with, and that error is distributed across lots of its parameters, it has a lot of potential to learn, right? It can modify itself to be able to find a key solution for the subspace. But once the model starts to converge to a solution, and it starts to kind of get comfortable with that solution, a lot of its learning has already been done, right? The only thing that can be done now is small, tiny little steps towards the improvement of the process. The solution for that is something that we call an annealing process, in which we synthetically, artificially increase the momentum of those weight changes, and that process allows us to kick ourselves out of low points, local minima, and up and over hurdles in a space, right? So if we get stuck somewhere where it's a plateau kind of between two ridges, we might want to have the system effectively get a little bit of momentum and rocket itself up out of the space. But what that's going to involve is a construction of some algorithmic process that contextualizes the adjustment of that learning rate parameter and the integration of an appropriate amount of that gradient in order to be able to determine forward momentum process. We can't just add a specific value to the weights and hope that that's actually going to cause something to change. Now, can we do that? Yes. It's effectively a random restart. If we go in and we just add some sort of masking values to the network, we can sort of add a little bit of a shake the box, right? Shake the box up. But still, ultimately, what's likely to happen is that when it starts to converge towards the minimizations of the local set points, It's going to lose its speed again. It's going to stop having that nice, that early process, right? That honeymoon period of the network where everything's great, everything's wonderful, right? And then after a while, everything started to kind of converge, slow down. It's not as impactful, and then the rest of the process is a slog, right? And even a lot of the rest of the process can be what? Overfitting at that point in time. So we're going to have to consider that if we have too large of a learning rate or too small of a learning rate, that overfitting may actually be an unforeseen consequence in both of these cases, right? Typically, it's actually too small of a learning rate that tends to incentivize the network to kind of find ideal positions within a larger manifold that can allow it to converge to positions that are not favorable for the reserve set for the validation. But we're going to use some methodologies to do this structurally, all right? So we say that a very high learning rate tends to cause what? Divergence with respect to the loss characteristics, right? The system just probably is going to go down for a little while, but then it's going to absolutely lose its mind, okay? This happens, all right? We actually do, like, this is like rampancy, okay? This is the thing where the AI, like, you know, starts just behaving erratically. AlphaGo, right? If you guys saw that one. Occasionally, whenever playing games of AlphaGo, it would spontaneously lose its mind and lose the game because it lost track. They literally had no idea the reason why it was doing this. And oftentimes they tracked it back to some of the learning rate characteristics that they had established with respect to how much it was able to update its belief system at a given time. Okay, so whatever it thought was going on with the world, and whatever it assessed with what was going on in the world was effectively an assessment of the gradients for the inputs that it was given. And if its assumptions about what was likely to happen in at the next stage, the next epoch of the process, were too off base, then it would diverge from reality, right? It would imagine a board that could not exist, you know, or a configuration that could not exist based upon some unexpected turn of events. A low learning rate does what? It takes a long time to converge to a solution, okay? But ultimately, it does converge to a solution. It's just going to take a lot longer to do so. But it's not always the case because this does not necessarily guarantee that it will ever converge to the values established by the good learning rate. Too small of a learning rate can get lost in local minima. So this may actually be the model getting stuck here, right? Rather than continuing the trend and converging with the good learning rate output. Ultimately, here's another consideration. If the system starts overfitting somewhere back here, right? Then we have this idea to say the maximum performance that is established by the network will be reached by a better learning rate before overfitting, right? Rather than and less than ideal learning. So if you remember some of the ideas we talked about, kind of parameterization and parameter flexibility and penalties that we're enforcing for multilinear regression operations in statistical frameworks, right? This framework relies upon us to have a good understanding of the appropriate amount of the gradient to add relative to the ability of the model to converge to an ideal solution. Now there is a paper that I just read recently, and I mentioned it to you guys, I believe last week. I'm on the fence, okay? It's a relatively complex paper. Not gonna lie about that. But I think I'm going to go ahead and assign it to you as a reading activity. I gave you guys the previous paper, the LeCun paper, to look at. This one I actually think I want you to read through because it's an interesting concept. They have taken many networks, all right? Many of the common ones, VGGs and RCNN operations, etc., and they have compared their features, the features that are most significant to their decision baselines. And they claim now that even most of the mainly significant convolutional networks are effectively exploring the same relatively low dimensional manifold with respect to their convergence. So effectively, all of these different models are going to come to almost the same end case conclusion, but by a very different set of roundabout processes, right? It's kind of these little spanning arcs of the way in which the system learns. And the paper has these beautiful little color projections of these arcs and systems. And it explains to you, at least at a certain level, how they used principal component analysis to extract the meaningful features at lower dimensionality to compare the network performances together. That notion to say that many networks with different topologies, all right, we call those architecture components, they broke down what the most significant factor was with respect to the end case performance for those networks. And they found out that architecture was number one, and that things like batch size and learning rate characteristics were actually less significant in the capacity of those networks to train to ideal positions. But at the same time, they were still components of the process, all right? So they said they did make an argument that the learning rate relative to the topology was actually a fairly tight linkage. So there is a relationship between the way the network is put together and the learning rate with respect to how well that learning rate fits this good learning rate consideration. Notice there's no specific values assigned here, right? It doesn't say, if you set your learning rate to 0.0002, in all cases you'll get a good output. No, that is not truth, right? There is not a number that fits it. In the same way that no two networks are effectively the same as if they're not truly analogous to one another, right? If they're not totally homologous networks, then we're going to have to say that even one change of the number of nodes within the network can change the way in which gradients with respect to those error surfaces are computed. So every time we add a node, what happens? We have a number of weights that are added to the system that now become a component of a high-dimensional manifold for the error estimation. As we add coefficients to the system, we're increasing its flexibility to fit, right? So what we ultimately want to do is we want to say, hey, don't get too crazy with any of these parameters at any given time. Don't try to adjust for all of the error relative to any one given component. It is a type of regularization, but we'll talk about our regularization strategies that we apply even over top of this to try to drive down the total weights throughout the system, right? We even use some methodologies to penalize the weights themselves. So one of the things that we can do to help overcome the problem that we experience with singular, right, sort of monotonic characteristics with respect to the learning rate is to implement something that we call learning rate scheduling. Learning rate scheduling effectively says, I'm going to set up some predefined sort of parameter characteristic that starts off, which we say the first case we would like to have what? I'd like to have a nice big learning rate. Okay, the goal is for me to get as close to the wall as possible without running into it. I can take some nice big steps to start off with, right? But I should not keep taking these steps as I get closer. What should I do? I should slow down, right, as I'm getting closer and closer to the wall. The idea is if that's the overfit wall, or if that's the parameter barrier of some performative metric that we're interested in, we should start approaching it much more slowly as we get towards it. Now the interesting portion is we're already taking into consideration, as a result of the gradient, how much error is left. So we already know how far it is to the wall. We're just going to rescale the step size as some fraction thereof as we're approaching that distance reduction metric. We don't want to take whole bytes out of all of what's left of our error all at once, because here's the real consideration. Since it's spread over so many different weights, any given one of those estimates could actually be fairly wrong, especially considering the fact that it's likely that there will be a change in the change of the gradient somewhere in between where we are and where we're going to end up going. Since we only established the gradient over that tiny little infinitesimal fraction forward and backwards from our current instantaneous location, we don't know what's going to happen to that gradient to the surface as we get closer to that error point. So taking too big of a step as a result of too short-sighted of an estimate of the remaining error within the system is going to do what? Increase the error. It actually makes it more wrong, because you can only incorporate a certain amount of the estimate of local error contribution for that weight in that dimensional space. The higher dimensionality it gets, the worse that problem becomes, because we are doing it equally across many different dimensions, the hyperdimensional manifold. So if we say every single weight gets treated the same way, then we should start off with something that seems relatively high initially. This seems like a good option, right? And then falls off at a reasonably consistent rate relative to some consideration. So strict scheduling operation might take into consideration the baseline process of annealing, in which we reduce the learning rate over a period of time, right? And by reducing the learning rate over that period of time, we say learning rate decays. Okay, so this is an exponential decay factor. So we've included another exponential, right, on top of all the other exponentials and characterization. We now have another curvature that's coming in. We have curves acting on curves, acting on curves, acting on curves, okay? It's crazy. It's crazy how many things we're now calculating for descent and operations. So the gradient descent slows this slows the gradient descent integration, right? So as the gradient slows, if you have a slower learning rate, then you're going to get a less rapid learning rate processed eventually. So this idea of decay kind of makes sense to us because we say as you're converging toward the solution, slow down, take smaller steps, things may actually get more complicated as you get closer to the ideal solution. What we notice is that the first few miles are easy, right? But the last couple of inches is the hard part to really tease out all of the remaining parameterization, right? Get a lot of knobs to adjust, and getting everything just right, fine-tuned into that last little bit of error is actually the hardest part of the system. So cranking it down and taking into consideration an even more localized, linearized approximation of the relationship between output and error is going to be an improvement over our current consideration. We can use an exponential or cosine decay system to gradually reduce the learning rate over time, right? In comparison to what we were doing previously with the notion of standard annealing operation in which we use epochs. So interestingly enough, these two things may actually change from one another, because occasionally what can happen is a network will actually increase in execution rate as it goes through the system, because error propagation is smaller due to a couple of reasons. We'll talk about those as well. Because once some of the weights actually get reduced to zero, what happens to them? They're eliminated from consideration. If we are penalizing some of these weights relative to learning rate operations, then it is possible that some of them will fall to zero, right? Both the weight it falls to zero and its instantaneous gradient. So what can happen is those neurons will be what is called ablated. Effectively, they're burnt out. They don't become part of the system any further. Once they're burnt out, we don't use them through the backprop, so the network may start off fully populated, right, and then may become what we call sparse, because only some weights are remaining through the system as they are being reduced to zero, because those features have been considered to not have a significant relationship to the forward propagation process, right? You are the weakest link, goodbye, you're not contributing, right? So L1 regularization is actually what would be most likely to contribute to an ablation. We can use other tools where we even randomly ablate weights, okay? So we also use mini batching, which we'll talk about right toward the end of this. But using a learning rate process in which we're going to just decay over time, we'll take into consideration runtime constraints, or we can utilize whole epochs before we change our approach, meaning that we're going to go through a certain number of update cycles before we reduce the learning rate. So how we schedule it, the timeline upon which we schedule it, is going to be a consideration of the process. We can reduce the learning rate as well by a constant process, such as halving or some other system in that case, or we can use a validation loss stopping improvement operation and say, I am going to reduce the rate of learning if I have a certain number of checks that effectively fail with respect to external performance. So once the model starts to potentially indicate that it might be overfitting, we can say, hold on, slow down, don't make as many adjustments per batch, or don't make as many adjustments per sample. So if we say, I'm going to stop you from making as much adjustment per sample, then maybe we can tame it back from continuing to that troublesome trend of overfitting, right? Memorization of components. So utilizing that methodology of a validation-based approach to doing an adjustment rate system might be considered what's called a patience factor, which is sort of how long we're going to let the system persist at potentially creating that characteristic divergence between training and validation sets. The last one is we use a learning rate warm-up process. I've seen this one used a few times, but it mirrors the training admissibility of the network. So the network starts off with calculating the error, right? And then we calculate the error in some detail, and then we'll gradually increase the amount of locally computed value, which gives us a really good idea around the very beginning local space about what the gradient looks like relative to our initial starting position. Once we have that idea of good direction to go in, and we've sort of explored our local space, we'll be able to find the ideal hill up out of whatever valley we're in, right, for performance expectation. So this idea of sort of a small scale local exploration, start in your home, go around your neighborhood, go around your city kind of area, and then take on a more, globe-scaping, globe-trotting kind of approach. That's where you have this gentle ramp up, and then the process gradually slows down as the system begins to get a better understanding of global optimization properties. I think this one works especially well whenever you have somewhat low dimensionality search manifolds, and it probably works better for smaller networks overall, but I have seen something akin to this utilized with large scale neural networks, okay? So gradient descent with momentum, which is part of what we were talking about with the atom mechanism, is we're going to utilize the gradient descent process with a learning rate operation, but we're going to implement an understanding of how far we moved in the previous case. So velocity with respect to the system, right, indicates the weight for change at time t-1 plus some scaling factor alpha relative to that Lagrangian operator of the instantaneous gradient, right, for the weight accessorized relative to that t-1 position, right? So this is the current conditions, and then we're going to do some update process that we're going to take the previous weight considerations relative to a rate of change consideration for the previous update, right, with respect to the previous velocity. So here's the idea behind this. If the ball is already moving forward, we're going to keep a little bit of its momentum regardless of the gradient that's being computed. So if the gradient becomes higher, we can keep that same amount of momentum. This is a decaying characteristic that actually models the process of mass being applied to the weight. So we apply some mass to the weight. Once you get the mass rolling, what happens to it? It's harder to slow it down. So if it's already moving at a relatively good clip and it hits something in an area where it's relatively flat, it will stay rolling on the flat area in the hopes that it will get past the flat area quick and go down another big trough, right? So this term, V of t, is considered momentum, and we derive momentum by this process. All right, I'm not going to go through it in excruciating detail, thank God, right? But if you really do want to understand the proof behind this, this is the idea that we can establish to any degree of steps for the past several sequence gradients, right? We can determine the relative rate of change at previous steps. So this is kind of how much of the previous velocity characteristic was being kept in place. This is the fall off operation with respect to that gradient at the previous series. The t-2 step, and then back to the t-1 step. So it's going to not only keep track of how much of the gradient was being incorporated at the last step, but the last several steps. So this is a bit of a register that kind of keeps track of what the gradient has looked like around its space. So it informs the system about it gives it a memory, right? It gives it an understanding of, wait, where did I come from? What did where I came from look like? Because ultimately the gradient is calculated how? Exactly in that spot. If I don't tell the system explicitly, you were here before, and this was the gradient you experienced at that point, and this is how much of the gradient you choose to integrate at that point, it forgets, right? It doesn't know that. It doesn't have a history like we do in our heads. We have to build it a memory, and so we're popping a memory off to the side of it and telling it to what degree that information is going to have notoriety, usability for us as we are incorporating future spaces. So keeping track of some of the previous change in value with respect to the rate at which the weight was moving on that gradient surface is just keeping track over a certain period of time of that kind of like a leaky integrator with respect to the previous gradient. It keeps a small amount of the previous gradient to keep the system alive. Okay? This Nesterov system is the accelerated process of momentum characterization. And Nesterov accelerated momentum utilizes a slightly different set of scaling factors with respect to keeping track of the weight at the previous time scale, as well as the predicted characteristic of how much of the previous state velocity was kept, okay? So it says, not only am I going to tell you how much I moved last time, but I'm going to tell you how much of what I kept from the previous time step was actually being scaled in there as well. So we have a learning rate effectively to say how much of momentum is conserved, right? How much friction. That's effectively what we're talking about with respect to the Nesterov system, is that as we begin to get closer to a system that has some degree of gain unit, we begin to notice what? The vector of the gradient, the component which indicates the steepness, right, the rate of change relative to the instantaneous update position. We've been thinking about this primarily of saying, do we move forward or do we move backwards? But that gradient also contains the component of the estimated likelihood or estimated rate of change for error with respect to that update. So if we got some improvement between step 1 and step 2, and we got what we expected, right? If we expected we'd get this much and we got it, then we're going to maintain confidence that that portion of the gradient was a good amount to incorporate. But as you move down to the edge of the system, what happens to it? It starts off with a relatively high value, high magnitude with respect to the component of change estimation for the gradient. But as it's moving down the surface, what happens? The slope changes. So the change of slope becomes incorporated in the relative confidence of how much the relationship between the rate of change and the expected output is going to be incorporated, such that we don't get a ringing operation. Where if we keep our momentum here, we'll keep jumping larger and larger spaces with larger confidence, incorporating more steps to get to the ideal solution. By incorporating an understanding that we're going to have to be more conservative at each step of the process, we may be able to estimate a smaller local instantaneous gradient change and adjust for what would have been a much bigger adjustment in the previous step by scaling down a small amount of momentum with respect to the rate of change in the magnitude of the gradient vector. Everybody tracking with what I'm talking about here? Okay. This one's kind of cool because of the fact that it allows us to create a much more robust understanding of how the change scaling is happening. So a much less, the other methodologies of sort of just using numbers for learning rate characteristics and just pushing them down seem very primitive at this point in time. Why aren't these used more commonly in most cases? They're computationally costly, very computationally costly, because we have to calculate that, we have to keep track of memory. Not only have to keep track of weight, we have to keep track of the gradients, we have to keep track of now the past 3 gradients for every single weight, and then we have to calculate those at every single update step. I would just go over here, okay? Let's just, like, who cares, right? Like, this, if I had to take an extra step or 2 on this side, theoretically, both of them end up in the same place, right?
Right.
So if this one costs a lot more to compute, unless we have a lot of resources that we're not really utilizing, then this might not necessarily always be the best case. But because of the fact that it does have this consideration of a much better understanding of the gradient, If this gradient was more complex, then we might get a significant capacity toward being able to find an ideal global minima, right, rather than getting stuck in a local minima when this space becomes more complex. Because if I'm moving down for quite a while and then I have a saddle point or a hip space or a slight plateau, and then I have a drop off, right, but maybe a sharp pushback up and then another drop on the other side, I could come down this and literally jump all the way to the other side and get stuck in this local minima before ever exploring to the center. So if we have this system where we're slowing and we don't jump over quite as far, we'll get to explore the whole bottom of the surface a little bit more cleanly with the Nesterov mechanism, right? It preserves a little bit of an understanding of the prior gradient considerations and makes adjustments about the amount that's being integrated per update process that has just a slight amount of calculated iteration update for approximation in future space. All right, what are some of the other tools that we're going to utilize? Everybody's familiar with this one, right? Mm-hmm. Anybody that's done even the remotest amount of data processing will understand that you probably ought to perform some type of normalization on your data. Now, in many cases, whenever we're going to get up into some of the more complex spaces, we're going to start utilizing image normalization techniques, which are going to start employing different kinds of filters. Now, there's a lot of those filters that are out there, but most of the time what we're going to do is we're just going to rescale it such that the absolute deviation of the system meets this characteristic for the distributional elements of the intensity of the image frame, right? So typically, what does an image frame have within it as far as values? 0 to 255, right? From no intensity to full intensity. And each channel is represented by its own grayscale representation. So if we normalize per channel versus normalizing across all channels for intensity versus normalizing across the whole system of channels for standard deviation within the entire data set, it might even be a little bit more difficult to calculate these considerations. That makes an instantaneous amount of sense, right? It is going to be contextually based. Where you choose to normalize and what factor and feature you choose to normalize with, how many samples you're normalizing across, those are going to be considerations you're going to have to take into scope with your data, right? So do I normalize within the sample or do I normalize across the samples? These are the classic questions. You know, these are our Hamlet moments, to be or not to be. So we utilize a mean subtraction process in order to zero center the distribution, and then we'll utilize a mechanism for division across the standard deviation in order to be able to compress the representation space and take out of consideration some of the spread that can be characterized by variance with respect to the space characteristics here. So within a scale operation for some type of visual data space, on pixel intensity operations, you put them between ranges of 0 and 1, or as the case is given here, divided by 255 in order to make the image effectively binary, right? So your either highest intensity or lowest intensity might be one mechanism to characterize, or as we're considering across the average intensity for the images, we might want to try to get the system to be a little bit more fair such that all the images are always compressed across the same relative amount of pixels of a certain intensity across the sampling. One of the reasons why this can happen is because when the kernel is multiplied by the image target, what happens? It's a quantity, right? If there's one really bright pixel in there that correlates with that convolution operation, it's going to be a very high intensity response. If one image is a lot brighter and a lot sharper than the other image, then the image that is brighter and sharper is going to be considered to have more value and more weight and more data information in it, right? So we have to treat every one the same way such that we create the same relative distributional characteristics in all the images. We normalize them so that all of them look the same. You're fairly familiar, I mean, imagine all of you understand the concept of audio normalization. The amplitude of the audio across two different tracks can be normalized such that it ramps or sets the limits on the upper and lower bands of the system to crunch it within a specific range of interest to stop you from getting blown out of your headphones, right, whenever a song of different genre starts in between the two. So the normalization creates relative, similarly intensity across the system, such that each of the samples carry the same relative informational weight, despite having some distributional characteristics as individual samples within the system. So we utilize this mechanism to be able to work with both standard data that we're going to bring in as feature characteristics for fully connected networks, right? And we can even incorporate normalization layers within a network, right? To be able to characterize and adjust for the spread of features extracted from existing visual data. All right. We talk about this notion of gradient descent. Actually, these two slides should be reversed to one another, but I'll go back to this for a moment. We talk about gradient descent. One of the considerations that gets put into play is oftentimes FC networks, we can treat the entire system as one big data set, right? So go through every sample and then backdrop, right? But in reality, it's far less efficient to do that, and actually far more potentially dangerous and costly from the perspective of potential overfitting to train on the entire data set at once. Instead, we're going to do something that I've talked about beforehand that I'm trying to provide you with some specifics on operation preferences and definitions now, right? Sometimes I've talked about some of these things at a sort of a, here's a concept kind of level. Now I'm trying to make sure I provide you with, clear definitions and expectations for this. But the consideration here is that if I update a single parametric update, one back propagation across the entirety of the loss for an entire data set, there are many, many points at which I could have potentially stopped, updated, and learned something from the few that I had already looked at. So by breaking up the data set into a series of smaller groups that the system has to try to adapt to optimally for that subgroup, it treats each individual subsystem as its own data set. One of the things that's interesting is if you have multiple data sets to train off of, then the system has a very hard time overfitting to any one given data set. So if these batches, we call them mini batches, if they're selected from a larger system, we can have hundreds or maybe thousands of samples within them, right? In order to be able to stop the system from finding one specific sample to memorize, which can occur whenever all samples are incorporated. What's the other problem that's given up there? ImageNet has 14 million images in it. They ain't all fit in memory, okay? Not even remotely, especially not in GPU memory. The GPU memory is going to be a much more significant constraint, especially as there are two competing objectives within GPU memory. So we've talked a little bit about how this idea that the GPU is kind of this extra computer you install in your computer, right? It has its own memory, its own processors, everything else. What also has to happen on the GPU is I have to copy the network to that memory. So actually the arrays that represent the transforms and the weight components of either the convolutional or fully connected network that we're attempting to run also have to be in that same GPU memory. So if the model gets too big, right, there's not much room left over for samples. So whenever I very first started training some models, I had a 6 gigabyte GPU. I had a model that was 4.7 gigabytes, right? The max batch size I could get was about 24. Okay? It was all I could shove in there toward the end, right? Yeah. So the batch size wasn't dictated by any sort of like arbitrary thing that I came up with. It was just how many I could shove into the GPU at the end, right, and still make the thing work. All right, so that's a consideration as part of the reason why we started doing this. Yeah. Is just out of necessity. But later on we realized, hey, it's actually kind of a cool thing. Whenever you're only showing it a few at a time, then it can't keep track of the one that came five batches back and says, hey, I wanted to fit to that one really close. I really wanted to keep the information from that one. And it says, look, hold on, you've got to try to fit these, right? Forget those. Forget worrying about that. If you adjusted a way to try to characterize the small deviations in that one sample, no, it's gone, right? Focus on the ones you have in front of you. And as a result, it keeps this sort of moving goalpost, if you will. This is the interesting part of it. If we keep moving the goalpost, the system will not overfit. So by having individual mini batches with their own variances and deviation characteristics, it's effectively like if we'd gone out and collected multiple data sets from the real world, right, independent data characteristics, and they were treating them like k-folds. This is a very interesting component that correlates the notion of k-fold validation and mini batching, and the effect that k-folding's original purpose was to try to characterize the optimal fit for a specific model complexity. In this particular case, we say if we characterize, we're going to train it on all of the k-folds of the system, and we're going to just keep showing it a new one every time. So the order changes such that for every new system in which you've gone through the whole data set, you can randomly reselect a new group of mini batches, and then each of those batches is a random recombination of components within the system. So it has a little bit of the advantages of k-fold cross-validation and a little bit of the advantages of the bootstrapping for showing what different kinds of distributional mechanics can exist within the data sets that are being trained. Whenever we look at this for operative gradient maximization, we're looking here of saying it's probably best for us to use relatively small updates sizes here whenever we're doing smaller mini batches. Why? Because if I have too few examples and I have too high of a learning rate with too much momentum in it, what might happen is I take this group of samples and then everything shifts over based on that group, right? And then the next group shows up and you go, everything has to shift back, right? So shift over, shift back, shift, and it's just everything ends up just getting constantly shifted around because too big of updates are happening based upon too little information. This is actually one of the things that can happen when we talk about the idea of biases from a sociological standpoint, right? You say, I have problems with someone of a certain cultural ethno background, right? And it's because I had a bad experience with someone like that one time, right? That's how bigotry starts. Is because we had too much weight put on too few experiences. So too much individual affectation towards those anecdotal examples can generate that idea of a certain type of systematic bias that we're looking to overcome. Yes, John?
So my question is, the gradient uses the learning rate, like if it uses the learning rate large, right? But in the mini batch, can we make it smaller learning rate so that it will be good? That's my question.
Well, whenever you're doing a mini batch process, what I'm saying is if you have a preference,
small?
Yeah, you can. I mean, you can set it, right? So you're going to set the batch size. It is an arbitrary size. You're going to select that parameter. We can utilize tools externally to maybe sort of k-fold through a series of architectures or subsets of the system in order to be able to determine the architecture that might be ideal for that, or the batch size that might be ideal. So interestingly enough, sometimes we'll actually start off by exploring the space of a network by varying the batch size. We'll look and say, try 100 epochs, try 5 configurations at 100 epochs for ranges from 10 samples per batch all the way up to 64 or 128 samples a batch by factors of 10 or something like that, right? So you let the system autonomously train through stepping up, running a few samples, averaging them, stepping up, running a few samples, averaging them. And what you'll find is that within that first little bit of the network, right, those first 100 or so epochs will tell us a lot about what's happening, right, and what is likely to happen in the output case. For really complex networks that take tens of thousands of epochs to converge, even that small little bit of information in the beginning can be relatively enlightening to us as we say, hey, at 70 samples per batch, we started getting a really good, it was just big enough to encapsulate enough variance for the system to learn from, but not so big as the system had potentially the capacity to try to overfit to any one given subdistribution. Right, so as a result, we can parameterize and we can do what's called that hyperparameter optimization in that same way by going from a meta perspective to analyze the performance of the model as we step through changes in those parameterizations. The real problem becomes when you have 10 different parameters to mess with, right? And so you have to do this grid and you get this like 3-dimensional 10-dimensional thing, where you're like, this changes with respect to this other thing, and now you're doing what? Now you're doing analysis on the analysis of the data. So we call it meta-analysis, right? So we're doing a meta-analysis. So I have seen this is truth. They have neural networks that select the parameters to train other neural networks.
Oh.
Because you can look at the efficiency of the model with respect to the change and the change of performance increase relative to things like learning rate and batch sizing. So if the outputs of the network were hooked up to the parameterizations of the network, then you start off by backpropagating the quality of that selection of parameters in order to be able to change to an ideal selection of parameters in the output case.
Oh.
Crazy?
Yes.
You guys are all like, that's fine.
I mean, it's not crazy if you think about it.
Well,
I don't
you
know.
start doing it, it is.
Yeah.
You guys tell me that now until a week into the project, and you guys are all like, I don't want to do this anymore.
I think
Yeah.
actually doing it would be
I'm
chaotic,
thinking it,
but,
and
like,
it's
Okay,
going to
we'll
be
talk
fun.
about this idea
In terms
of
of-
stochastic search
Ah.
versus grid search operations.
Fucking shivers.
Neural network.
Okay, we talked about this
Oh my
idea of
God.
normalization, right? So we say, what if we want to do this normalization on a global scope, right, initially? But we said sometimes maybe the outputs of a system have feature characteristics that tend to overemphasize certain elements. So we want to have the features that are being handed off to the next layer also normalized so that no one given feature gets over-incentivized versus another, right? This is a mechanism for establishing regularization between layers of a system. So a batch norm can actually hand off the normalization between layers of a component system. And the funny thing about this is it causes the system to not emphasize too few components too much, right? This is another sort of regularization technique in the effect that normalization tries to push the whole thing down such that the significance is spread over as many of the feature components as possible. So we say that the informational characteristics, since they're spread wide within that variance space, utilizing this sort of zero mean unit variance normalization characteristic alleviates the problem with initialization, improper initialization frameworks for parameters and hyperparameter frameworks, okay? What do I mean by improper initializations? I mean, you started with the wrong learning rate, or you started a learning rate that was too high or too low. So this batch normalization process attempts to somewhat mitigate as the elements are being traded off between the systems of a convolutional network for maybe too aggressive or too optimistic of learning rate updates or optimistic of kernel distribution updates. The other characteristic too is that some kernels may be really good kernels and some kernels may be really crap kernels, right? If you only care about the really good kernels and the really crap kernels get left behind with respect to the value and significance involved in them, what happens? You're actually doing a dimensionality reduction process because you're dropping many of the features along the way, because if they have low intensity or low relative intensity in terms of their activations on the output layer, and you don't normalize them in order to try to create uniform activations across the entirety of the kernel space, then you'll end up with a problem. You'll end up with only the most ideally positioned initial configurations of the kernel, those weight matrices, right? Only the weights that are most aligned with the actual understandings of the ideal configurations will end up being utilized in the next layer, right? They'll end up becoming the most significant features that get passed off as the inputs to the next. So keep in mind that at every layer of a system, every major module layer, the output at that system becomes the input of the next layer, right? So the output of one system is the feature of the next in this bucket chain of processing. So if we incorporate this batch normalization process between the trade-off sequence, we insert the norm layers immediately after the convolutional layers because we want to put them in between the convolutional layers and the activation state layers. This is an interesting part. So we actually take the neuron apart, and the summation elements, right, the weights times the inputs, the normalization goes in between there and the activation module. So the normalization layer is in a really kind of an interesting spot within the space. We have to decompose it. Are you going to want to try to build one of those yourself? No, because the architecture components to be able to do this are nasty. Do we do this in here? No, because Kuros will take care of it for you. Okay, you can pull a batch norm layer, right? TF, initialize, batch layer, okay? That will do all the things you need. So we understand how this works, and we're just going to create kind of a special kind of neuron that takes into consideration the relative intensity of the inputs, tries to scale them a little bit more uniformly before the system gets handed off to the activation layers. They are very common in convolutional neural network architectures, right? Such that we probably are going to have one in between most of the layers, most of the CNNs to activation layer before pooling operations happen. If we normalize before pooling, this is an interesting portion. The features should still hold up, right? The most significant ones will still pool. But once we normalize, it will make everything a little bit more fair, such that the localized elements of the activation are more likely to get picked up in the feature-preserving dimensionality reduction process of the pooling layer, right? The smaller version that contains the most highly activated components, if we normalize across the array of the components to get a better overall uniformity of distribution, then when we rescale, it's going to be more democratic, right? Everybody has a chance. But when only a few of them that were most highly activated and ideally distributed are utilized as the most effective, then you're going to get a really realistically interesting outcome, and that is the system will stop learning very quickly. Why? Without this normalization, systems will often converge to a minimum and just stop, plateau. If you understand this component of it, you'll understand kind of everything that's going on involved with it. Let me explain it to you this way. If only a certain number of the kernels that were initially initialized, right? So the initial configuration of those kernels are the ones that are extracting pattern and feature information from the images. Those are going to continue to be the only features that are going to keep getting propagated forward in the system, right? So if those are the only features that keep getting propagated forward, the system will actually keep disincentivizing the inclusion and the utility of the other kernels, right? They're going to have their gradients are going to keep getting messed with and fidgeted with. But the significance of and the weights of the activations for the kernels that were already ideally aligned with the patterns are going to keep being more significant in the output layers of the system. If a certain number of features within a specific space are incentivized as being the only features of merit or significance, then everything else effectively gets ignored, and that means there's no additional information to pull in. That means that when you initialize the network, it either initialized right or it initialized wrong. Without normalization, there is not going to be any way for the system to control for the distributional characteristics of the initialization. So every time you restart the training process, you will converge to a different local minima, right? Because different features will get extracted, and the system will prioritize the initial configuration. Remember we talked about the notion of sensitivity to initial conditions? We said that if a certain network has a very low learning rate, that it could take a really long time to converge to the ideal solution. So if we look at it from the perspective of saying that if one network gets randomly initialized and it's in a relatively good position, right, it can still converge to the solution. But another network that's not initialized quite so well with respect to the space, right, sort of starts off in a bad spot over here. It's never going to be able to get up over this hill to get down into this valley on this side, right? But the network that started over here can fall into it relatively easily. So the dependency on initial conditions is very prevalent in this space with we're talking about the normalization as a mechanism to try to make it fair so that a unbalanced initialization, right, guess what? The system will have an opportunity such that the other features can have their say too, right? So even if their activations would normally be low, then we're going to normalize their inputs such that their activations become more distributed more evenly across the activation output. So as a result, even low intensity or low frequency feature characteristics are still going to get propagated forward. They're still going to be considered valuable to the system with respect to passing it into the next layer. Everybody track with me where I was going with that? Mostly? 40%? 20%? Okay, we'll look at this. Honestly, this is one of those things that once you start doing it, if you compare a network that doesn't have it to a network that does have it, you'll kind of notice what happens to the weights, and you can see a few of them along the way. Okay, one of the methodologies by which we improve model performance overall is this ideal of validation-based early stopping. Have you guys heard of this before? Okay. By using a mechanism of a previously reserved validation set, this is different than the testing set, this is a third set, we're going to assess the potential future performance of the model utilizing this validation set. This is actually identical to the notion of a validation set assessment in K-fold, where one fragment or one segment of the training data gets broken off and treated as an internal testing set. So when the network is training on the remaining training data, it will check every now and again against the performance of the validation set. Interestingly enough, we can't just use the training or the testing set to do this. The reason why is because the model gets exposed to the value of whatever the performance is of this data point. Guess what? It can incorporate that in the updates. It's sneaky like that. It only needs to know the error relative to the validation to incorporate that error with respect to the updates of the local gradient. It will still compute the error of anything that's running through it. The backprop step will still be run, it's still possible to be run by the network. So it will have latent information about the validation step performance because we're feeding it back that information. So the validation set will actually attempt to, or can attempt to, try to adjust some of the training parameter characteristics based upon how well the model is performing with respect to validation. We talked about that with respect to the local instantaneous gradient, but we also said there was a possibility of utilizing the performance on the validation set as a mechanism to attempt to adjust the learning rate as well, right? So now I can adjust the learning rate if my validation starts to diverge from it heavily, or if it starts to increase over a period of time, right? So from sample 1 to sample 2, if the value is up, and then sample 2 to sample 3, the value is also higher, and then sample 3 to sample 4, the value is also higher, we would consider that 3 relevant failures for validation. We'd say it fails at the validation test, and with a certain number of validation check failures, we will consider the entire validation check process to be complete, and we will stop the model before it continues training in order to stop it from doing what? Overfitting.
Overfitting.
There are n number of samples that we utilize for the number of validation check failures that we're tolerant of. We call this patience. Sometimes the system can get caught in a relatively intense local minima, and will have several epochs worth of failures with regard to the validation before it finds a new process of weight adjustments that become more generalized, right? So it'll get stuck optimizing based upon a few training samples, and then all of a sudden it will break through to a new layer of understanding, and we'll get a massive reduction in both validation and training performance. At that point in time, we reset the counter and we let it play again, right? So being a little patient, having this patience factor at play, allows us to be able to have a little bit more time to let the network potentially converge to a realizable set of outcomes, okay? Because it can wander around for a while not understanding something, and then all of a sudden it can wake up and go, I got it. I combined these two things together, and now all of a sudden I understand a lot more than I had. This is one of those things that we call like breakthrough learning, right? This breakthrough learning process is when the model goes from looking like garbage for a while and then all of a sudden has this radical drop in error as a result of a few subsequent evaluations, because what? With regard to the hyperparameters of the error surface,
maybe several of those values all kind of found their own drop-off points in a relatively steep region of that manifold, and now they're all optimizing and balancing much better with regard to their outcomes. Okay. Weight decay driven regularization is that process I was talking about of saying how weight decay and momentum characteristics can be utilized to regularize the performance of the system, and the effect of saying that it tries to get the model to be more general rather than very specific. So by having a model that's more generalized, we get a model that has a more smooth curvature, and this actually implies what? Probably more realistic of the natural world. Very few systems have these sharp transitions in contrast to operation. Similarly to what we were looking at whenever we saw something like, think about like a K nearest neighbor approximation. This would be like, say, like a K of 1, right? And this is a K toward like 50 or something like that, right? So the factor lambda that we utilize is the decay operation is a mechanism by which we try to drive down the parameterization characteristics of the network. So we say, hey, everybody gets suppressed just a little bit in terms of the amount that we're going to allow any individual weight to sort of take off within the system. So if everybody continues to decay based upon how much of the gradient they're integrating, the weights will actually continue to reduce. This is a little bit different than just learning rate consideration. This is over time a weight will continue to drop. So a weight itself will have both the learning amount that it's integrating for previous step to next step, plus a scheduled operation to where if that weight has not been activated recently, it will decay over time. So this lambda factor is a mechanism by which if you fire together, you wire together, all right? That's one of the principal notions of neural networks. It's called the Hebe hypothesis. The second component is if you fail to fire, you die. So over a long enough period of time, if a neuron fails to fire, the body will stop supplying it with nutrients because it considers it to be unnecessary because it's not involved in the rest of the neural chain sequence. Similarly, the weights, if they aren't contributing to the process, they will be starved out. So these are a mechanism by which we say it is very similar to the construct of the L1 regularization, in effect to say that the neuron can be pushed all the way down to 0 with respect to its weights. The difference is the relative value of the coefficient is not the consideration. It is not how large the weight currently is, it's just how long it has been since it was effectively used. So more weights, highly complex network originally, the system eventually starts to level out, average out, the entropy of the system finds an ideal configuration such that the network is still at the same level of connectivity, but now approximating a lower level of complexity. This might ultimately be related in somewhat to the spline characteristic in the effect of, if you remember, that as we increase factor lambda with the spline characteristic, what happened? We're using some of that second derivative with respect to the change in the value of the component within a region, all right? If we push that down, we can have a higher order system that becomes more linearized, and so we have effective degrees of freedom. So while there's a potential for the network to take on this configuration, by utilizing a weight decay process, we can make it approximately look like this configuration by forcing some of those weights down as their utility becomes less and less valuable as their frequency of activation drops over the runtime network, okay? This effectively is, yet again, another mechanism, another penalty to attempt to stop the network from overfitting. That is an overfit consideration there on the left-hand side, right? And this is potentially an underfit characteristic. So this one is probably closer to ideal consideration, right? Even though this one may be sort of optimally generalizable, this one encapsulates and characterizes more of the unique characteristics of the positioning of the samples within the data space. So we want to get it down to a degree of incentivization, right? Say, hey, try to treat everybody fairly, but not so much as to completely tamp down the actual significant components. In that effect, okay, I'm going to say that it is actually kind of closer to the L2 regularization, right? The ridge regression notion, because we want to incentivize the network to push down towards 0
but not go all the way there. So depending on how high you set lambda here will be the difference between pushing into sort of a L2 versus an L1 style regularization. We can full-on use L1 and L2 regularizations to accomplish these normalization operations, layer-based normalization operations. That is effectively setting that factor lambda. L2 is much more common than L1 regularization with respect to networks. It's been shown to actually have significant better performance in most cases because of the fact that it's hard for the system to know on any individual instantaneous basis which of the weights are going to be significant to subsequent layers throughout the forward process. So this is mostly a penalty that happens with respect to the forward process, right? That normalization incentivizes the constraint of the outputs that are going to the activations to try to make it more distributed. So as a result, it doesn't necessarily understand how those features will be considered in subsequent layers and their utility to the final answer in that case. So most of the time we find that out by backpropagation. So this is actually an interesting relationship here. We have to have a balance between regularization operations and backpropagation and learning rate update optimization. So the reason why you see this gets incredibly complicated at the high level, but once you start doing a bit of this, you're going to get a little bit more comfort and flexibility involved in it. I'm probably going to have to start reducing the windows for some of the tasks we're going to be doing. We're going to be doing stuff, we're going to be doing projects that are going to be like a week or 2 weeks worth. All right, but they're going to build on each other. I'm working out now, we're going to start off with comparing FCs to CNNs from a couple different task cases. And then we're going to work on implementing some higher level CNNs. Then we're going to move on to implementing some autoencoders. And then eventually we're going to be doing some transfer learning. We're going to take pre-trained models, apply those to new tasks or new data sets, and then we're going to compare those potentially, trying to find a good activity for this, but I'd like to see maybe if we can play around with some GANs as well. Okay, the only limitation there is they take a while to train, so we might have to try to see if we can transfer a GAN as well. So transfer learning, which is probably going to be one of the most common things you'll do right now in the field, will probably be part of what we make up our last major project in the course for. Okay? Thank you guys, I'll see you on Thursday. We'll pick up from here, I've got a couple more slides in a second. We still need to finish our semantic segmentation section. I've always